Today we're going to be solving systems again, but this time we're going to use a different method. The last time we used the substitution method, and today we're going to learn about the elimination method. So, reminder that a system is a bunch of equations that are all on the same plane. They're graphed together, and what we're actually solving for is the intersection of where all of these equations kind of meet up. And with the substitution method, we were able to solve for one of the variables, either solving for x or solving for y, and then with that, we plugged it into the other equation, effectively replacing either x or y, whatever was solved, in order to make it so that we just had one variable to solve for, and then plug that into the other equation to get both x and y. Today, we're going to be using elimination, where we'll be adding and subtracting entire equations in order to match up the x's and y's and get it so that we're down to one variable again. So it says here, to solve a system using elimination, get the coefficient on x or y to exactly match, then subtract the equations and solve. Alternatively, you could get the coefficients on x or y to be exact opposites and then add the equations and solve. So let's do a few examples. For the first one, I've got two equations. Equation A is 3x plus 2y equals 12, and the second equation is 3x minus 4y equals negative 6. What I need to get are the coefficients on either x or y to exactly match or to be exact opposites. Here, I see that they match exactly for x, 3x, 3x, which is great. So since they already match, I'm just going to go ahead and subtract these equations together. When I do that, I'll see 3x minus 3x is going to go to 0. And what I'm left with, 2y minus negative 4y, subtracting a negative, so careful with your negatives here. That's going to make 6y equals 12 minus negative 6 is going to be positive 18. Now let's divide both sides by 6. And I'll get y equals 18 divided by 6 is going to make 3. Now with this, I can go and plug this into either of my original equations. It doesn't matter which one because this is a system. They're all working in conjunction with each other and I'm finding the intersection of them. So let's just do probably equation A since it doesn't have a negative in it. So I'll go over here and I'll say A is 3x plus 2y equals 12, except now I know y equals 3. So this is going to be 3x plus 2 times, replace y with 3, and this is equal to 12. 3x plus 6 equals 12, and subtracting 6 from both sides, I'll get 3x equals positive 6. Finally, divide both sides by 3 to get x alone. And I'll have my solution x equals 2, y equals 3. Now what this means is in this system, if I were to graph this, I would see that these two lines are going to intersect at the exact coordinates 2, 3. In fact, let's take a look at that. So here's Desmos, and my first equation, let's activate that, is going to be this red line right here. And the second one is this blue line. Normally, we would just graph one of these at a time, but because this is a system, I'm going to turn both of these on, and you'll see that these two lines do intersect, and their exact intersection is the point 2, 3. X equals 2, y equals 3. And that's what you're solving for. Now this one was pretty easy because 3x already lined up with this 3x. Let's look at one where it doesn't do that to start off with. In this problem, I have these two equations. Equation A is negative 2x plus y equals 9, and the second equation is 4x plus 3y equals 7. Clearly, the coefficients on x don't match. This is negative 2, this is positive 4, and the same thing for the y's. This is a positive 1, this is a positive 3. So when you come across a problem like this, what you need to do is multiply one of the equations and manipulate that equation in such a way that those are going to now match or be exact opposites. In the first one, I saw a positive 3x in both of them, so I was able to subtract those equations together. Here, I'm going to be a little clever about this. Instead of a, let's find 2a. So if I multiply everything in a by 2, I will get the following. Negative 4x plus 2y equals 18. And I'm just going to rewrite b right underneath. Positive 4x plus 3y equals 7. And from this, you can see that by multiplying a by 2, I was able to get the coefficients on x to be exact opposites. Negative 4x here, positive 4x here. When they're the same sign, such as positive 3x, we subtract. But when they're opposites, I'm going to add the equations together. Because when I add negative 4x plus positive 4x, that'll go to 0. And I'm left with 2y plus 3y will make 5y equals 18 plus 7 is going to make 25. Let's divide by 5. And we find y equals positive 5. From here, I can take y equals 5 and plug it into any equation within my system to find x. So let's do the top one here. Negative 2x plus y equals 9. I now know that y equals 5. So negative 2x plus positive 5 equals 9. I'm going to subtract 5 from both sides. Negative 2x is equal to positive 4. And finally, let's divide by negative 2 here. This will get x equals 4 divided by negative 2 is negative 2. This means that this system has an intersection for these equations at negative 2, 5. Let's take a look at that one too. So I'm going to bring back Desmos. Again, here's the first line. Here's the second. And we see they do intersect. That intersection takes place at negative 2, 5, which we found algebraically. All right, one last problem. In our third example, we see we've got 2x plus 3y equals negative 1, and 3x minus 5y equals 27. Nothing matches here, so coefficients on x aren't the exact same, nor are they exact opposites, same with y. And in addition to that, there isn't anything I can easily multiply just one equation to match the coefficient for the other, meaning like in number 2, I was able to multiply the first one by 2 in order to get the coefficient on x for A to match the one that was already on B. Because I can't do that for number 3, I have to multiply by the other equation's coefficient, meaning for A, I look at the coefficients. This has a 2. This one has a 3. I'm going to multiply A by 3 because 3 is the coefficient on x for B. So this will be 3A and then 2B. If I multiply A by 3, this will make 6x plus 9y equals negative 3. And then multiplying everything in b by 2, this is 6x minus 10y equals 54. Now I see that I've got 6x and 6x. They're exactly the same, and so I can subtract. The x's will go to 0. I'm left with 9y minus a negative 10y. Careful with your negatives here. That's going to make positive 19y equals negative 3 minus 54 is negative 57. Divide both sides by 19. Y equals negative 57 divided by 19 is negative 3. All right, now I'm going to plug this y equals negative 3 into any one of these equations. So let's just do the first one again. 2x plus 3y equals negative 1. Plugging in y equals negative 3 here will be 2x plus 3 times negative 3, and this is equal to negative 1. 2x minus 9 is equal to negative 1. Let's add that 9 to both sides. (2x) equals positive 8. And finally, divide both sides by 2. X equals 4. That means my solution is going to take place at the coordinate 4, negative 3. And let's take a look at that one. Here's the first line. Here's the second. And I'll see that they do intersect at the point 4, negative 3. So this is a second method to solving systems of equations. Next time, we'll be talking about how to solve systems with 3 equations and 3 variables.